Hi everybody, my name is Anibal Azevedo, and now it's the last class, the class number 7 of the track number 4 of how we can build an artificial intelligence technique applied to a container port logistics. So this is the last class of this track, and we finally get all things together. So we're gonna explain how we can use all the knowledge from previously class, and even in the moment that we see the developments that we made in the previously class, we're gonna say, oh, this code was explained in this class. Okay, so let's see the whole code. So just before doing this, let's see. I already have all the necessary code. So the approach of this class will be very different from previously class, since uh, we will not spend time writing code, because we've done this in detail in previously class. So we're gonna get an overview of the code, and remember that in the description of this video we have all the code, and this code is available for free. You just click on the link and see the Google Colab that we shared. Okay, so here we have, first it's important to use the previously developments that we made in previously tracks. So we're gonna need the container ship class development that we made in track 1, and here we have the code, and the result not showing here. I don't know why, but it's completely working. Okay, so we clicked here, we just clicked here and activated this class container ship definition. So it's all working, it's everything okay. So, and what else? Here we have loaded also the code that we made in track 2, which is the unloading and loading rules functions. So we here have in detail tested all unloading and loading rules. Okay, and finally we also loaded the port simulator, and this is very important, since this will enable us to evaluate each candidate solution. Each solution that we propose will be evaluated by calling this CS simulation class. Okay, so that code is the final code that we made a lot of developments in track 3, and this is the last development. So all we activated all things, right? I don't know why this is taking too much time. Let's stop this. Sometimes we get some weird things in programming that we can explain. That's it. Not stopping. Okay, not stopping. So, and what is more, it's important now. We got this code, and this code here is basically all things together. But before describing all these things together, we're gonna get a great overview of the code. So, with instead of defining uh, particular methods, for example, we have here this function crossover, we have this function mutation, and so on. So instead of defining uh, just define functions, we made a class and put all these functions inside this class. So we have methods. Okay, so this class, the name is genetic algorithm class. And the first thing here is important, is the constructor method. And this constructor method use the same strategy that we made, that we used in the track 3. Remember that in track 3 we have this CS simulation, and we used this very interesting way to pass parameters. We used named tuple. Named tuple is a very interesting thing because instead of passing a lot of parameters, we just use a name, and inside this name we have a lot of variables that we call parameters. So let's see, for example, here in this CS simulation, we have this parameter, simparam, simulation parameters, that we received this. Obviously, before calling the constructor of the function, we have to define each variable to the simparam, and when we finally defined all values, all parameters inside this simparam, and put this simparam to this variable s, we pass it just s that contains this variable and this second variable, this third variable, and this fourth variable. So the strategy here will be the same, okay? So we made this for the port simulator. I really recommend you to sit in detail this because we spent a lot of time explaining this, okay, in this track. So I will use the same parameter here, but not simparam. I will use another name, gemparam, genetic algorithm parameters. So we have bounds and number of bits, number of iterations, size of the population, crossover rate, and mutation rate. Okay, so these are the parameters that we need to define how the genetic algorithm will work. So this is very important because, as you can see here, the genetic algorithm constructor method will use not only the genetic algorithm parameters that this will need also the parameters to the simulation. So not exactly the parameters, but an object to the container simulation. So this is an object that remember us how the simulation will work. So this simple line contains a lot of information. So let's see how this works in detail. Also, in this constructor, we have to define the population as an empty list, okay? Because the population will be not just a list of lists. Each individual will be a list, okay? So let's see how we call this method, how we call the constructor of this class. First, we have to define a number of rules, 2 unloading rules and 6 loading rules. This will be the class to the container ship, the constructor. It's a calling to the constructor of a container ship object. And this is the transportation matrix that, that we explained in the previously videos. And also, we have this verbose method, verbose parameter. It's false because if you are interested to find errors or a detailed execution of the program, you can use it as true here, okay? So you're gonna get a lot of messages, but if not, if it's false, like we have here, it only appears the this message print, only this, okay? Very simple message. uh, Also we have to define the simporan, as we talked about. Simporan, it's it's a kind of named tuple that will contain all parameters necessary to just simulate a solution, to see this a proposed rule, how many movements of the container ship will be necessary to do if you apply a specific sequence of combination of rules, okay? So this is the C07. So we defined this object as an object of the class C container ship simulation. So it's perfectly defined here, and it will be very important to call the genetic algorithm. So let's see the next parameters here. We have genetic parameters. This will be the number of combinations that we can apply to each port, the number of rules combination. We have the number of ports, okay? And using this information will be very important since we're gonna define the number of genes. This is the number of rules combinations that we can apply for each port. For example, if you have 4 ports, we're gonna need exactly 4 elements in each individual. This individual will have 4 places where they should decide which combination of rules will be applied in each port. Okay. So finally, what is this? This is just the bounds of the values of the combinations. For example, you have 12 combination of rules. The lower bound of the number of combinations of rules will be 1, and this with the number of combinations, 12, for example, will be the upper bound. Okay, so let's see if we can see the result of this. It's not appearing. Okay, so that's it, the result of this. And the number of iterations, as we can see here, eventually we can change this way of counting iterations. We can count start from 1 and end in 10. Not a real problem. Okay, so this is the number of bits. So you have here as number of ports, as we call it before. This is the size of the population. It's not a great size of population. It's not necessary. And this is the crossover rate and the mutation rate computing using this. Okay. Okay. So finally, we can get all this information in a named tuple. Name it as gen parameter. Gen param. So we are just putting all things, all information inside this name, gen param, and storing this in a variable called m. Just this, okay? And we will pass the object to container ship simulation here, and also pass the parameters for this genetic algorithm class with using this variable m. And that's it. We calling the genetic algorithm and just make out work by calling GA iteration. And it's magic. The magic happens. Okay, let's see how this magic happens. So this was very important because we were not interested to make a great confusion. We have to configure all things before calling the function, before constructing things. And that is the principle to get all the code organized and understandable, I hope. Um, okay, so let's see what we should do here. So was we are just talking about how the constructor method works. Okay, so when we call GA, this method was called the self.m and self.thing will have the values, the necessary values. How we can recover these values to use inside the methods. So let's see. We call it here. Let's see in the sequence of the execution of the program. GA iteration. So we should call this method GA iteration. So iteration, how we can recover the data that are inside the self.m, the gem param, okay? So self.m, we can recover by using self.m.bounds. So we just used a short name, bounds, any bits, and inter, and population or pop, air cross, and air mutation. So it's a smart thing to put a more simplified name, because inside this method will be very difficult if you still using this very long name. Okay, it's not very long, but it's a little bit long when we put inside the command. So when we get all this, we just start self initial population. So initial population we already talked about, and we can see the development. I really would like to recommend the developments that we made here, because we explained it in very detail in the video of the class number 2. So it will occur somewhere explaining in detail. Obviously we didn't made here a function, but all the ideas to use that we employed in this function are just in these 3 lines. Okay, so that's very simple, but it's important to understand what we are doing, here. Okay, so we call it initial population, and we get what we got when we call this self initial population. What we will be returning. Remember that we don't return anything here, and we doesn't have a return because we saved this information in this variable self.pop that contains all the population, all individuals. Okay, so it's a list of lists. Each individual, as you can see here, it's a list, and this is the combination of rules that will be employed in port 1, 2, 3, 3, and 4. So this is the initial population. Okay, not exactly this, depending on the parameters that we are using, but this is the idea. Okay, and what we got after we doing this? Okay, since we have this self pop, we already have an initial population, initial list of lists. So we fixed the first element of the list, the first individual. We will save as best individual, and the evaluation of this individual will be stored as the best one. Can be or can be not. Okay, we don't know, but we save it just to test in the next code lines. So how we can get the evaluation of this individual? We should call the object self.sim.evaluate. So remember that when we do this, in fact, what we are doing is just to get this simulator. Let's see the simulator, and call this method evaluate. And this method is exactly a way to count how many movements we're gonna spend when the ship perform its travel to ports using a certain combination of rules. Okay, so what's important? How I can know the the combination? What is the combination of rule that we are testing? The combination of rule that we are testing is just this. When we do this, we are just getting this list. Okay, we pass this list. Remember that we're gonna use a translator method, a decoding method here, translate number to rules. So we applied this many times, and this translates the a certain number, integer number, into a series of numbers. And when after doing this, we combine this series of numbers in terms of names of unloading and loading rules. Okay, so that's the interesting part. We are just getting in deep the code. Now the code is making sense because we made the project to all things work together. So that's it. It seems to be very simple, but it's not. We made a lot of effort to make this seems to be simple, but not simple. Okay. Okay. Now, after doing this, we just get one solution. We believe that's the best because we seen nothing better than this. This is the first one. But we can improve it. How we can improve this? We can evaluate more solutions. So to do this, we're gonna get Jin in range and enter. So this loop is to make a series of times evaluations, but not only evaluations. For example, we get all the population self pop. So we're gonna get all this list of lists. Okay, we got all this, and after doing this, we're gonna get each list of rules. We're gonna evaluate and store all these evaluations in scores. Okay, so after doing this for this A in range and population, so we're gonna see each score that we got here and see if this score is lower than the best that we find, the first one. Okay, I know that we are evaluating to the second time the first one. We can avoid this uh, computational work, but it's okay. It will works also. So we are just taking seriously to make the code as simple as we can, although sometimes it will make some extra computational effort, but it's not a serious problem here. Okay, so now we're gonna take this best, and if we get this situation, we just have another solution, another individual that has a better score than the best one. That until that this program until this moment the program find this best, but we can just find another individual that has a better score than the actual individual. So we're gonna change your concept of the best individual and just print, oh, I find a new best individual. So after doing this, what is interesting is to apply a kind of selection. So this is a very important moment, since we're gonna select the individuals based on scores that they have. So we're gonna take all the population, okay, and see these scores for selection. Let's remember that we find this in the you can find this selection method in detail in the class number 4. So occur will appear. We detail we made a very detailed description about this, how this work. But basically, it's okay. I have initial population, so but I can select more frequently the best scores. Okay, so that's the idea of this line. And when we got all the selected individuals, okay, so now they can produce a children. What's a children? It's a combination of the best individuals, and this combination can be made in two ways. First way, so here we have a combination that we're gonna need two individuals to make a new one. So it's the crossover, okay? So you can find the detailed explanation of this method in class number 5, where we talked about crossover, how this works. So here, for example, we take two individuals. For example, we took this and this. So we selected at random two individuals, okay? And finally, we selected also at the handle a crossing point. So this individual will has a crossing point here. We change this information with this information, and this information will be replaced by this. So they are crossing informations information. So this will generate two children, and this we made this uh, for half of the population. We're gonna combine, and also it's interesting to say that we can apply crossover, and also we can apply mutation. So when we call mutation, we can see here at class number 6, this is the mutation method. For example, here we made just this number, this bit, okay, just this gen, and it's a totally random number, but this number should be between the bounds in terms of combination of rules, okay. So this is the all the way, and you can say, okay, you are showing the code in another notebook. Where is the definition of these methods? Okay, we have here. We have defined inside this class. We have the initial population. We have here the strategy to get from this m and number of population bounds and bits, and replace it by a short names, okay. So this is the initial population we're talking about. We have the selection, it's here. The problem is not the short code, but understand how this is working, okay. We have the crossover that we explained in previously class how this works, and also have the mutation. As you can see here, we have this trick to recover the crossover rate, and also have to make all the same thing to the mutation, but with an additional information about the bounds. So this is the thing that we need to create to use the methods that we defined, that we explained in previous class. After doing this, after doing this loop, remember this, we repeat this kind of, okay, let's produce a evaluate the population, and see if there is someone that's a new best solution. Select the best and change the best using crossover and mutation operators or methods. And finally, print a kind of report here of what's happening in terms of fitness and iterations and individuals. What's interesting here, the fitness is exactly equal to the evaluation that we made using this container ship simulator. And the reason of this is very simple, because if we minimize the number of movements, we are just minimizing also the fitness. Sometimes it's not the case, this case. Sometimes the objective function of the problem is to maximize. So the fitness, if we are trying to select the best fitness, uh, just should apply some equation or formula to adapt to select the best fitness. Okay. Let's see if we have some other issues here. Okay. No. So finally, when we finish this loop, we get the best and the best evil, and we should return them. We should return, and this is precisely these two variables, best and score. So we didn't print this, but we can print the best and the score. Let's execute this code. Uh, so it's interesting to see that's working. We already executed this, okay. So let's see if it's working. Okay, it's very fast. and it prints the best and the score. So the best solution is this one, and the fitness, the number of movements that we're gonna made is this. We can execute this very fast way. Okay, so that's it, people. I hope you find this video interesting and useful for your application, your applications. You can adapt this structure to build your own problems, to solve your own problems. Because the general infrastructure is you have some problem, some situation, you model it in terms of simulation, and you can try to find a better quality solutions by using this genetic algorithm. So a genetic algorithm will call many times the simulator and to evaluate the solutions. But if you made a very smart way to compute, to simulate things, it will not spend too much time to get an interesting solution for your problem, an interesting alternative to your problem. So it's a very interesting way to solve things. And what we're gonna need in the next track, we're gonna need to incorporate at this framework another kind of equipment. That's it, cranes, because we can put, we can load or unload the container ship without using some special equipments. These special equipments are quake cranes that will be very important, since the quake cranes have a very specific dynamics which will impact in how much time we need to load or unload the container ship. So count the number of movements that we are making in a container ship is important, because each time you move some container, we're gonna spend a certain amount of money. But it's not enough, since we need to know how much time we are spent by doing these operations. Because if you take too much time by unloading or loading a container in a container ship, you can have some warnings from the port. Okay, you have this time window, and if you break this contract, you're gonna pay a very big fee. Okay, it's okay for you? No, it's not okay. It's a very big fee. So if you don't count, you don't plan correctly how much time you're gonna need to perform your operations, you just leave the port with the containers without loading or unload the containers. So it's not a good situation. And to avoid this, we will explain how we can incorporate in the simulation process the quake cranes, the dynamics of the quake cranes, and also we're gonna explain uh, how we can incorporate these dynamics in the simulator, and also we can how you can how this gonna impact in our in the whole program. Okay, so thank you for your attention. I hope you find this video useful and interesting, and see you in the next track. Bye.